Welcome everyone to this week Autonomy Talks. This week is a great pleasure to have with us Michael Hyland, who is an assistant professor at the University of California, Irvine, working in the civil and environmental engineering department. So something about Michael: he obtained his Bachelor of Science and Master of Engineering in Civil Engineering at Cornell, and then did his PhD at Northwestern University. And his research in general focuses on modeling and analysis techniques to support planning, design, and management and operations of multimodal transportation systems. In particular, he has been focusing on emerging transportation innovations, such as autonomous vehicles, and their impact on transportation systems. As you can see from the bio, he has won several awards and is part of many committees that are important in the field. And we are very excited to have his talk today, which is titled New and Old Network Models for Design and Analysis of Shared Mobility Systems. I personally am very excited to hear about this talk because this, for people that know, network models are a difficult topic. You might find many of them. Depending on the application, you might need a particular choice, and it's often difficult to, let's say, take wise decisions when dealing with these network models. So I want to hear Michael's take on this. So without further ado, Michael, go ahead, the stage is yours.
Thank you very much for the kind introduction and for the invitation. It's really great to be here. As was mentioned in my bio, basically my research area is modeling automated vehicle fleets, shared automated vehicle fleets in particular. My dissertation work was on kind of the real-time control and operation of those vehicle fleets, but I am in civil environmental engineering department, so we tend to try to understand the impacts of, well, a variety of things, including new technologies on the broader transportation system. So these two studies going to be presenting today are kind of the more high level. How can we use network modeling techniques for both designing shared automated mobility services as well as analyzing them. So I'm going to give a brief outline that's probably not super necessary on shared automated mobility and just a brief background on the basics of network modeling. Then I'll cover two studies. The first is a new model, new network model for creating shareability networks for shareability metrics for transportation networks. And the second study will be using an old minimum cost flow network problem to help do fleet size planning for automated mobility on fleets. So as a brief background, there's particularly in the US been a change over the past 12 years in the availability of modal options for travelers. Historically, on the non-private side, there was basically just taxis, fixed route bus, fixed route rail, and for some folks, what we call paratransit or van-based accessible transit. Over the past 12 years, I mean, there's been a lot of changing dynamics here in terms of who the players are, but we have a bunch of new modes. Of course, the two obvious ones being Uber and Lyft now existing, as well as Google Maps, an example of information communication technology impacting the transportation. So we put together this spectrum of shared mobility modes here. So on the left side, we have the fixed route, fixed schedule with high capacity modes. And on the right-hand side, we have the most flexible, yet the lowest capacity of the modes. So left-hand side, we have conventional fixed route, rail, and bus. And on the right side, we have what we call ride sourcing or ride hailing, effectively e-taxis, which include Uber and Lyft. And we have a range of modes in the middle between ride sourcing and fixed route and schedule. So a typical network model, of course, includes a set of nodes. These are also called vertices, and they are joined by a set of links. Another name for links are arcs or edges. I will probably use the nodes and links terminology today. So some examples we see are, of course, highway networks, telecommunication networks, and even things as complex as supply chain networks can be modeled in a network format. In a network flow model, there's kind of two main characteristics, particularly if you're doing flow-based models. Well, the links carry the flows, and of course, we have our conservation of flow at each and every one of the nodes. which is the sum of flows going into the node equals the sum of the flows going out. And the typical notation that I'll use is I'll use n for the set of nodes, and I'll use, well, I, j, and k to index the set of nodes. And then we can label A as our set of arcs or links. And well, there's two different ways that I like to label the links. There's this each individual link, or we can denote the upstream node and the downstream node of a particular link. Okay, so the first study I've been working on with my graduate student for over 2 years now, in which we're trying to develop shareability networks to describe at a very high level, well, shareability potential for a particular city or region. So as motivation for that, we have here 3 different, not to scale, but of equal scale road networks. So on the left, we have Paris. In the middle, we have Irvine, California, where I live right now. And on the right, we have Manhattan in New York City. So you can see that not only are the different structures for these particular streets, but also the density of streets in those particular networks vary considerably. So this is the kind of broad conceptual framework we're coming into, not just this study, but really this, let's call it research agenda. That is, there is a relationship we're hypothesizing between urban form, the land use, and the socio-demographics of the people working and living in a particular area. You can think of that as a city as a whole or different subregions of a city. That impacts directly the road networks, but also the spatial temporal travel demand distribution, where people are starting their trips, where people are ending their trips. And you can also think about these as more complex activity travel chains. The current focus of this study, what I'm going to talk about today, is the linkage between these 2 parameters, that is the network, road network, and the spatial distribution of travel demand, and this set of metrics we're calling shareability or potential for shareability in a particular city or subregion. What I'm not, well, what we haven't done yet, but working on right now, is making another connection, which is the connection between the shareability metrics and you can think about it in 2 ways: the viability of different shared mobility modes from that spectrum I showed earlier, or the optimal or the most likely to be successful shared mobility mode. With the hypothesis that some regions that are, high density roads, high density population would be most likely to support the high capacity fixed route transit. Whereas in more, not necessarily rural, but suburban areas, fixed route, fixed capacity transit might not be the best mode, or you might want to move along your spectrum towards more flexible in terms of route and schedule, but lower capacity shared mobility modes. Okay, so the goal broadly is to create metrics, particularly ones at the network level, that capture the shareability potential of a particular region, given these 2 inputs. The specific objectives include both defining and formulating a fundamental unit of shareability, which we're calling the flow overlap. And we want to extend that fundamental unit of shareability to the network level. And here's where we formulate our maximum network flow overlap problem, or what we'll abbreviate somewhat inconveniently MNFLOP. We want to also consider the detours that travelers have to make when solving this maximum network flow overlap problem, in addition to just their overlapping with each other. We want to use the output of this mathematical network-based program to create shareability metrics at various levels. So not just for the entire city as a whole, but also looking at individual origin destination pairs. Is there a lot of potential for shared mobility modes? And even at the link level, we're going to look at, is there a lot of demand here to support this high capacity fixed route, fixed schedule transit service? And then finally, with this talk, right, in that last slide I showed the focus of our study, we want to not necessarily validate that shareability potential metrics we're developing here can be used to design shared mobility modes, but we at least want to verify a few things. The first is that MNFLOP does increase flow overlaps compared to shortest path assignment. We also want to be able to differentiate between different demand patterns in a particular network in terms of their shareability potential. And then one thing we're particularly interested in is this node level metric. So for different nodes in a network, how much overlap or how much shareability potential is there, considering both the magnitude of demand from that node as well as the directionality of demand. Okay, so what is flow overlap? So we're going to define it at a unit flow level. So think of a large network, think of an origin destination pair and a unit of flow traveling between that origin and destination. The flow overlap is what we're saying is a average number of other trips or flows along the path that traveler makes, where of course we're going to weight by the length of the links that the traveler traverses from its origin and destination. And these other trips in which the person is going to be overlapping with come from, well, its own origin destination pair, of course, but also every other origin and destination pair or a pair of nodes in the network. Let's look at this visually. So on the left-hand side, we basically have the same network and the same demand. We have traveler X going from A to D, traveler Y going from B to D, and traveler Z going from C to D. The numbers in the links are the link distances. On the left-hand side, we have all the travelers going along their shortest path from their origin to their destination. And on the right-hand side, we have them, well, excuse me, we have two of them detouring from their shortest path to a slightly longer path in order to increase overlap on at least one of the links in the network. So this is the formulation for flow overlap for a particular unit of flow or a traveler from origin O to destination D along a particular path K. I already went over that A is the set of arcs or links in the network. C sub A, I have cost here, but you can think of it, I think, more effectively in terms of distance. So the distance of a particular link, the length of a particular link. We have a link path incidence matrix, which makes the connection between a particular path on a particular origin and destination pair and whether or not that path actually traverses link A. We have a somewhat complicated, for now, let's think of it as an input parameter, but I'm going to make it endogenous later. The number of other travelers that are on link A from every other origin and destination pair besides the unit flows origin destination D on a particular path K. And then we have this FOD -1, which is the last term in the equation up there, which denotes simply all the other travelers that are going to be going from origin O to destination D. And by, well, construction or definition, the unit flow from O to D is going to be overlapping with every other flow from O to D. Okay, so as was pretty obvious in the example before, in this first scenario, where all the travelers take their shortest path, we have no flow overlap in the entire net. Every single traveler travels independent or without overlap with all the other travelers in the net. In the second scenario, we actually do have some overlap. So traveler Y, who's going from B to D, their entire path overlaps with the two other travelers. So maybe you can see my mouse here. Their flow overlap is 2 units. Whereas travelers going from A to D and C to D have 0 overlap on the first leg of their trip, that is from A to B and C to B. But then they have 2 units of overlap on the second component of each of their path legs, which is 4 out of the total 7 units. So on average, they overlap with 1.14 other travelers. Okay, so that's flow overlap from a unit flow perspective from well, not a single origin destination, but at least a small network. So we want to expand this to the network level to calculate how much flow overlap there is for a particular region. So again, we have our same set of inputs. We have our graph or a network. We have our origin destination travel demand table, and we have another input parameter we're going to create is a finite set of acyclic paths between each origin and destination. So I guess at the limit, this could be a very large number for k, but we're going to actually use a relatively small number for k in order to handle some of the computational challenges associated with the problem formulation. And then we want to find or select the paths for flows between each and every origin and destination pair that maximize total flow overlap in the entire network. We're going to add a second term to the objective function that allows us to capture the trade-off between this flow overlap measure and the detours that travelers between origin and destination pairs have to make. So we're also going to assume that all the flow or all the trips between an origin and destination pair are assigned to a single path. Okay, so here is the objective function of the maximum network flow overlap problem. Hopefully you remember we just defined exactly what Z sub ODK is. This is our overlap metric for a unit flow going from origin and destination OD on path K. We have a second component of our objective function associated with origin and destination OD and path K, which is the detour relative to the shortest path. So if the travelers from O to D have to go on a slightly longer path, maybe their detour distance is 1 mile or 2 miles or 1 kilometer. We have a W parameter here, which just allows us to vary the importance of detour relative to flow overlap. The XODK here is our decision variable. So for a particular origin and destination pair, are we assigning these travelers to path K or are we assigning them to a different path? So we're going to sum over all the potential paths for a particular origin and destination pair, and then multiply that by the demand from each origin and destination. Sorry, my daughter's saying hello. So in the previous slide, I just used this Z ODK formulation. But if you remember, we had a more complicated formulation for what Z ODK is. As I mentioned, our kind of main decision variable is the path choice for flow from every origin and destination pair. We also have a set of auxiliary decision variables, is what I'm calling them, which is the flow on link A from every other origin and destination besides the one of interest right now. And I show on the next slide exactly how we calculate that. We only have a single, well, we have two constraints, one on the next slide and one on this slide. That's, of course, we must assign the demand from each and every origin and destination pair to one and only one path. Okay, so how do we calculate these auxiliary decision variables? Well, basically, we use a pretty simple formulation. We sum all of the flows from all other origin and destination pairs OD that are assigned to a particular path K, in which that path K traverses link A. So we have an issue here that this is a quadratic programming problem. So the term right here becomes very complicated because it includes decision variables for each and every other one of the origin and destination pairs, in addition to our current origin and destination pair of things. Okay, so my expertise is not solving quadratic integer programming problems. So fortunately, optimization software Gurobi does have a package that can handle constrained quadratic integer programming problems. So we make use of that to solve the problem on, let's say, medium-sized networks. We're going to see examples here from the Sioux Falls network, and we've also done slightly larger networks. We use the Network X package from OpenStreetMaps in order to do a lot of our network-based calculations. And in our inputs, we're assuming that we have 5 acyclic paths between each origin and destination pair, and we use Yen's algorithm in order to calculate the K equals 5 shortest path. Okay, so let's look at some computational experiments. So on the right here, we have the Sioux Falls network. There are 24 nodes and 76 links. We're going to look at 4 different scenarios. I'm only actually going to show results in the first 3. Scenario 1, we're going to have 6 nodes in the north of the Sioux Falls network, where we're assuming the demand is originating from. And we're going to have 6 nodes in the south of the Sioux Falls network, where we assume that the demand is going to be terminating. In the second scenario, this is kind of our origin-based analysis. So we're going to look at each and every one of the origin nodes individually, and we're going to have demand from that origin node to every other node in the network. We're going to do that 24 different times. The third scenario set is where we have 1,000 trips. We're going to look at particularly 3 different scenarios in scenario set C, where we have the same origin nodes. I believe they're going to be in the north of the network, and we're going to have 3 different sets of destination nodes. Some of those are going to be the central business district, or as we model it here. Some of those are going to be in the south of the network. And in the third case, the destination nodes are going to be scattered throughout the entire network. So we have these shareability measures or measures of overlap at different levels of aggregation in the particular network. Kind of our fundamental unit, again, is the trip overlap for a unit flow from origin O to destination D. To get the trip overlap percentage, we can simply divide that value, our trip overlap, by the total demand, either in the entire network or the demand between that origin and destination. The detour is relatively straightforward. It's the gap between the distance from the chosen path and the shortest path. We also have a metric called the marginal overlap, which captures the increase in overlap compared to the shortest path over, well, how much detour it's going to require to move from the shortest path to this new path from O to D. The node level overlap simply involves, for our base OD measure, summing up over all the destinations. Or if you want to do a destination-based metric, you sum up over all the destinations. For metrics like trip overlap, you move to node overlap, or trip overlap percentage, you move to node overlap. And then we also have metrics at the network level, of course. This was our average network overlap for the origin and destination pairs in a particular network. We have the same kind of idea where we're turning that into a proportion, the proportion of the network flow that overlaps. We have our total network detour costs for all origin and destination pairs. We have our average network detour ratio rather than ration. And then we also have our marginal network overlap and marginal network overlap percentage, which again are capturing this trade-off between increasing overlaps compared to shortest path versus increasing detours in the denominator compared to shortest. Okay, let's look at some computational results here. So we'll start with visual first. So on the left, we have what I'm calling MNFLOP, or pure maximum network flow overlap problem, where we ignore detour completely. In the middle, we have shortest path assignment. And on the right-hand side, we have what I'm calling by criteria, maximum network flow overlap problem, where we incorporate the trade-off between detours and flow overlaps. Okay, so on the left, we have, I think, probably an obvious visual result. The demands, or the flows, are concentrated onto many fewer links than the shortest path assignment in the middle network here. So this, as I like to say, verifies or meets one of our objectives, which is to see that MNFLOP actually can increase flow overlap in the network compared to shortest path assignment. And the by MNFLOP on the right-hand side is somewhat of middle ground solution between pure MNFLOP and shortest path. But in this case, it's much closer to MNFLOP than it is to shortest path assignment. Okay, so putting that visual representation into, well, actually these metrics we've created, we have this table here on this slide. And it basically confirms what we saw visually on the previous slide with the 3 different networks. That MNFLOP has a pretty significant increase in the average overlap, in the overlap percentage compared to the shortest path assignment. One particular interesting thing is that It's only a pretty small detour in absolute terms and percentage terms, but a 5% increase in detour across all travelers in this network compared to the shortest path assignment. And another particularly important metric is the marginal overlap. So how much does flow overlap increase per unit of detour? And we can see here that actually the by MNFLOP does better than the P MNFLOP. And that's actually, well, by definition in our objective function. We chose a value of 1800 for W in our by MNFLOP case, which ensures that this value is larger than 1800. Also have some results related to links. So this is average link flow on the links that are used. And we can see again that we have a much higher concentration of flows or demand onto links in the MNFLOP case compared to the shortest path case. So we also tried to identify the Pareto frontier between detour and flow overlap in this particular network with the same demand. What we do is vary this W parameter between, well, a very low value and a very large value. Once W gets down to about 0.1, we have the pure MNFLOP case, in which our average overlap is around 3,000 and the detour is around, well, 0.8 miles. On the other end of the spectrum, we have for W values greater than 3,000, we converge to the pure MNFLOP case where effectively detour is not considered at all. In this case, we have very, very little detour and around 1,800 units of flow overlap. I think I might have said that wrong. So this is the shortest path when W gets very large. We actually ignore the flow overlaps and we focus entirely on detours. Okay, so that's scenario one. Scenario two, you might remember, is looking at individual origins to all destinations. So I want to look at some simple examples first. So in this case here, we have, I guess I'll use the word scenario again, but 3 different networks. In all of these networks, we have the same total demand coming from zone or node A, that is 3 units of demand. But what we're trying to show here is that for the same demand originating from zone A, we could have significantly different levels of dispersion of that demand throughout the network. So on the left graph, or scenario one, we have high concentration or high shareability because all the demand is going directly from node A to node B. You compare that with the right-hand graph here in which we have, again, 3 units coming from A, but they're immediately being dispersed to 3 different nodes and 3 different links, such that there is, well, effectively, again, 0 overlap in this particular network. And then we have a middle ground here with the network in the middle. So I'll skip this and go right to the scenario results. So again, remember we're working with the Sioux Falls network. What each of these dots represent on the left-hand side and on the right-hand side are 24 different cases of solving MNFLOP, where for each case, so here we would solve from demand from node 1 to every other node in the network, and then would move to node 2, resolve the problem, so from demand from node 2 to every other node in the network. And of course, the main difference between the graph on the left and the graph on the right is the method used to solve the assignment problem, either entirely shortest path or pure MNFLOP. So basically what you see is, of course, a shift upwards from the right graph towards the left graph. So if you're doing MNFLOP, you can increase the overlap percentage in the network compared to the shortest path case. And then to look at that visually, we have 2 different examples here. On the left, we have demand coming from node 2 to every other node in the network. And on the right, we have demand from node 5 going to every other node in the network. I don't have the metrics here, but node 2 actually has higher shareability potential than node 5 due to the structure of the demand, the spatial distribution of demand coming out of node 2. So I guess I'll pause here and make a comment about the motivation for this study. My student Nav wanted to do this, where's the best location for ride sourcing services, for shared ride services, for kind of demand adaptive transit services and fixed route transit. And when we look in the literature, folks had done this. They had looked at where's the best case for demand adaptive transit and the best case for fixed route transit. Actually, Kanan might have been on one of those studies. I know her advisor did a couple of them. But the only input parameter they had for these studies was something they called demand density, which is simply the number of trips occurring in a particular subregion. And while we found that particular metric useful, we didn't think it was comprehensive enough. So we wanted to create metrics that capture not just the density of demand, but also the dispersion of demand, taking into account an underlying transportation network. And that's when we came up with these origin level shareability metrics. And what we think show, and what we're testing now with some other work, is that both total demand density matters and the dispersion of demand. So if you have an area where you have just a lot of demand, it can be quite dispersed throughout the network. You can still operate some demand adaptive transit services. But we also found that, or we're also finding that if demand is low, that's not a death knell. If that demand is concentrated in the network, that is, if it's going to mainly a few nodes in which the paths for those destination nodes are overlapped. So we're finding that both demand density and demand dispersion matter, and that the structure of the underlying transportation network also matters. Okay, last set of results here is scenario 3. So we have, it's called scenario set 3, where we have 3 different sub-scenarios here. We have demand from 6 nodes in the north to the central business district, which I believe is just nodes 10 and 11. In the second sub-scenario here, we have 6 nodes in the north to 6 nodes in the south of the network. So kind of these ones up here to these nodes down here. And in the third scenario, we have the 6 nodes in the north to 6 nodes randomly dispersed throughout the network. And then for each of these 3 scenarios, we calculate our many different shareability metrics. And what we found is, I think, what you'd expect. So when you have concentrated demand from 6 origins to 2 destinations, and those 2 destinations are spatially close to each other, we have the most overlap. We have the least overlap when our destination nodes are scattered. And then in the middle, we have the case where the demand is reasonably scattered, but we have some concentration of the trips into the nodes that are in the southern part of the network. The other metrics kind of basically confirm this. One thing I always like to look at is the marginal overlap. So for north to CBD, north to south, we have pretty close measures for marginal overlap. But for the north to scatter case, we have very low ratio of overlap trips to detour miles, which suggests that in this case, in order to get this maximum level of network flow overlap, we had to assign flows from origin destination pairs onto paths that required significant detours. And this is visually what's going on for these 3 different sub-scenarios. So you can see high concentration from the 6 different origin nodes to 2 destination nodes. I think pretty high concentration of flows onto links for the north to south. And then here in the scatter case, you can see we have a number of links with quite low demand on. Okay, so to conclude, what we showed is that this flow overlap metric seems like a reasonable measure for shareability potential in a particular network. We formulated this MNFLOP, which is a path and flow-based quadratic imaging program. An important thing to note is that MNFLOP is the way we've structured it, both mode independent and operational strategy independent. So it's, again, at a very high level. We just have where travelers want to start trips and where travelers want to end trips. We then decide, okay, what are the paths that would maximize their overlap between these origin and destinations? We just want to get a kind of high-level measure of the shareability. We also showed that, of course, PMNFLOP can increase flow overlap compared to shortest path assignment. We use the origin level shareability analysis to capture trip dispersion in addition to trip demand density. And then finally, I think with scenario both 1 and 3, we were able to show that these metrics actually can differentiate the shareability potential for a given network, which is the Sioux Falls network, but where we're varying the travel demands. That is, we're varying the demands from the origin to the destination. So for some future extensions, we are looking at developing heuristic algorithms in order to handle larger networks with more origin and destination pairs. We also want to use MNFLOP for a number of different things and ultimately designing shared mobility services. So the first is identifying these high demand corridors where there almost certainly should be, if not a rail transit, then maybe a bus rapid transit line. We also want to try to make the connection between, as I showed in the beginning, shareability potential, particular region or subregion of a network, and particular service design parameters. And then we also want to see, okay, so what if we just solve a bunch of vehicle routing problems for varying demand? Is our shareability metrics we created a good predictor of the performance metrics for the shared mobility service in which we solve the vehicle routing problem for? And then finally, I want to test the hypothesis, which is that cities in the US or cities around the world, which have, according to our metrics, high shareability potential, do those networks have high demand for transit? And of course, we'd want to use a statistical model in which we control for other factors that would also predict transit ridership. But even after controlling for these other factors, is there a strong association between our shareability metrics and the demand for transit? Okay. I did have a plan to go together a slide deck, but I think we're mostly out of time. Maybe I'll just run through that briefly.
Yeah, no worries. We are flexible.
Okay. Okay, so this study is pretty simple. We want to develop a model, or actually compare different models for determining the minimum fleet size for an automated mobility on-demand service. So brief motivation, why does fleet sizing matters? Well, put it simply, it impacts cost and it impacts service quality. A lot of the agent-based models that I've created myself and my colleagues at other universities have done suggest that fleet size is the biggest impact on wait times of any design parameter. And also from a societal perspective, smaller fleet sizes mean less parking space, which means we can free up space in our cities for, well, more productive things than vehicles sitting there throughout the day. So there are a number of other researchers that are working or have worked on the fleet sizing problem for automated mobility on demand. Many of them have used agent-based simulation approaches, including some of your colleagues at Zurich, Kai Oxhausen's group, and the Madsen folks have done this. So the advantages of this is that it's high fidelity, high resolution models, but of course we have the downsides of high computational cost. And in particular, these agent-based models are very data intensive. And since actual automated mobility on demand or vehicle fleets with automated vehicles don't actually exist yet, there isn't a lot of high quality data to support the estimation and calibration of those models. There are also numerical models that are in the literature. The state of the art, at least in my mind, is the path covering problem formulation by Vazifa and colleagues, which I'll cover briefly in a couple of slides here. So this is a really nice graph. You are welcome to look at the top 3 ABC, but I'm going to go over D here. So they're trying to determine what is the minimum fleet size for a set of taxi trips in Manhattan, New York City. The two inputs are the request. So this is the start time and start location of the request, and end time and end location of the same request. This is for, whatever, 100,000 trips in New York City. The other input are the travel times in the network. With these two inputs, they construct what's called a vehicle shareability network. The blue nodes in this network or graph right here actually represent occupied vehicle trips or passenger trips. So it actually includes the origin of the trip, the origin start time, and the termination start time and location. What the links represent, if there is a link between a pair of blue nodes, is that a automated vehicle can drop off this request and has time to pick up this request. That is, so if the drop-off time, let's say, is 9:15 for this one, and the pickup time is 9:30 for this request, this link indicates that the travel time between this location and this location is less than 15 minutes. So since these two blue nodes are not connected, that means that, well, they're spatially too far apart, spatially temporally too far apart. And then to determine the fleet size, what they do is solve a path covering problem. They're trying to cover all of the blue nodes here in as few paths as possible. So the answer to their what is the minimum fleet size in this case is simply 4 vehicles. This first vehicle was serving 1, 2, 3, 4, 5, 6, 7 trips, whereas this vehicle was only serving 3 trips. Okay, so advantages of this approach, they're actually capturing the network in, I'd say, very high resolution, but they kind of have 2 downsides in my estimation. A lot of their results rely on this maximum trip connection parameter, which just says how far a vehicle is allowed to travel from one drop-off location to another vehicle's pickup location. And the other downside in my mind is that these vehicles don't really have depots, and they don't stay in the network throughout the day. They just start at the beginning of one path and end at the beginning of another path, or and another drop-off, and then they disappear from the network. Okay, so what I want to do is formulate another fleet sizing problem in a time-expanded network using network flow formulation. I want to apply this model to a large-scale network, and I want to compare my model results, or the model results of my colleague or my students and myself, with this state-of-the-art formulation, and then analyze the impact of spatial temporal aggregation on our network flow formulation. Okay, so I'm calling this the time-dependent transshipment problem, or TDTP, which is pretty much a minimum cost flow problem for those of you that are familiar with network flow formulations. This is actually not an original formulation for fleet sizing in transportation. It is original for automated mobility on demand, but including my undergraduate advisor was doing this in the 1960s for empty rail car routing and fleet sizing. It's also been done for truck fleet sizing as well. So advantages: quite computationally efficient. Disadvantages, as that it does require spatial and temporal aggregation of a particular network. Okay. So the parameters quickly here. So we're given our travel times, we're given our distances between the zones we created. This parameter is probably the most important one. It's the imbalance of vehicle trips in a particular zone in a particular time period. So if we have this entire set of taxi trip data, we can calculate the number of vehicles that are terminating at zone I in time period T. And then we can also calculate the number of trips that are starting from zone I at time period T. The difference of those gives us our imbalance parameter FIT. A positive value of FIT means that we have, well, empty vehicles that we can use in our network, and we need to use those to serve the other zone time pairs that have a negative value for FIT. Some other parameters here: fixed daily cost of a fleet vehicle and the per mile cost of moving an empty vehicle through the network. I'm not going to show the formulation for the wait time because we assume that actually, like the path cover formulation, the wait time is 0. Then we have really just kind of effectively one set of decision variables, but I'm going to break that out into 3 sets of decision variables. So the first is the number of vehicles that start the day in a particular zone I. We're calling that YI. If you sum over all your YIs, you actually get your fleet size. We also have to model the repositioning movements of the empty vehicles through the network. We do this with the decision variable xijt, that is a movement of a vehicle from origin I with departure time t going towards destination j. And then we have zit, which is the case in which we are holding vehicles in zone I from time period t to the next time period t plus 1. And of course, our objective is to minimize cost. We make a few assumptions. That is, the occupied vehicle trips are fixed, which means that we're only controlling the empty vehicle trips in the network. This implies that actually the wait time for all the travelers in the network is effectively 0 because the occupied vehicle trips are fixed. There's also 2 different components of empty vehicle miles traveled that we want to keep track of. Our model explicitly captures what we're calling empty repositioning miles or trips, but there's also empty pickup trips. So we're going to be repositioning vehicles from one zone centroid to another zone centroid. But of course, not all actual trips in the network occur at the zonal centroid. They occur at other nodes in the particular zone. So our model doesn't explicitly capture this, but we do some either pre-processing or post-processing to get an estimate of these empty pickup miles. Okay, the problem formulation is shown right here. It's actually quite straightforward. Our objective is a combination of the fixed cost per vehicle and the variable cost of moving the empty vehicles through the network. So this is the decision variable to move empty vehicles from I to j at time period t, multiplied by the distance from I to j, multiplied by the cost per unit distance. The main constraint is the flow balance constraint in a particular network. It includes our holding vehicles from the prior time period to the current time period, and then holding vehicles from the current time period to the next time period. This summation term here is all of the vehicles from other nodes that are being repositioned into our particular zone time period of interest. And this term right here is all of the repositioning vehicles that are leaving our zone I at time period t. Have another flow balance constraint just for our first time period, which captures the relationship between our fleet size decision variables and our actual repositioning and holding decision variables. In order to ensure that the wait times are 0, we make sure that we have enough vehicles from the prior time period to cover the demand or the imbalance in our time period of interest t at a particular zone I. All right, so I'm going to show you a series of 3 different graphs, which is actually the problem itself. This, you can think of this as the raw inputs. This is the time-dependent origin and destination trip flows. So we have individual trips from our taxi data set. This says that there are 2 trips from zone I in time period 1 that are going to zone 2 that are terminating in zone 2 at time period 2. There's 6 from zone 1 in time period 2 to zone 2 in time period 3. So this is the, think of it as raw inputs to the problem. But we need to use those raw inputs to calculate our FITs for each one of our nodes in the network, where again, a node represents a zone time period combination. Our decision variables are the amount of flow that is going repositioning flow from one zone to another zone across time, or the number of vehicles that we're holding in zone 1 from time period 1 to time period 2. And in the solution or the output of our problem are the values shown here. So we actually only have one set of repositioning trips from zone 2 in time period 2 to zone 1 in time period 3. We have 44 repositioning trips. Our fleet size in this case is 20 plus 4 plus 55, which gives us a value of 79 for our fleet size. And then as you can see, we have a large number of vehicles that are being held in each zone from one time period to the next. All right. Just want to show one other set of results. That was a simple example. We did a large scale study for Manhattan, New York City. Different values for the spatial aggregation. We work with both census tracts and census block groups, and then different values for the temporal aggregation of demand. We work with 5-minute intervals all the way to 15 minutes. I just want to show the computational results, comparing our formulation, the time-dependent transshipment problem, with the path cover formulation. So let's just look at our two different spatial aggregations for TDTP first. So if we work with census tracts compared to census block groups, we see that there's a pretty big gap in computational time. This was expected. We think we can definitely drive down both of these values by doing some cutting of the network. But nevertheless, if you have higher resolutions for your zones, it's going to take longer. Sorry, census, I realize if you're not from the US, you might not know what census tracts and census block groups are. But these are just spatial aggregations. Census tracts are bigger than census block groups. And then if you compare our computational time with the path cover formulation, well, it depends on what your spatial aggregation is, but if you have pretty large zones, you can do much reasonably better than the path cover formulation. And one thing I'd like to note is that the computational time for the time-dependent transportation problem is independent of the number of trips in your network. Because our decision variables have nothing to do with the number of trips. They only have to do with the number of nodes in the network, where the nodes are made up of zones, spatial aggregation, and time period, temporal aggregation. Whereas path cover formulation depends entirely on the number of trips in the network. Okay, I'll leave it there, and I'm super happy to take any questions on either study.
Thank you, Mike, for the great talk. Let's now open the stage for questions. You can either write on the chat or unmute yourself and ask. I maybe break the ice and start with one question related to the first part of the talk. So I really like the fact that you can, with the method you presented, you can quickly assess the ability of different networks to allow shared trips. My question is, so here you considered shared trips in the sense that they share space. What about time? So I understand this is somehow a simplification to do an analysis, but have you thought about validating this with a time-dependent formulation? Let's say an agent-based modeling that really moves cars around, and you have time-dependent congestion and time-dependent demand and so on.
Yeah, great question. So in the paper, we even formulate the case where we have time indices for all of these metrics. But that's not really meant to capture the kind of within day dynamics. It's kind of like a quasi-dynamic model where you do what we've always done in transportation. It's like, let's look at the morning peak period. Let's look at the afternoon period. Let's look at the afternoon peak period. And I think actually that's all we want to do for this type of high-level model. I don't think that within day dynamics are going to be that useful. But I'm going to talk about validation. So what I actually like to tell my grad students, we haven't validated anything yet. We have verified that our model does what we say it's going to do. But we need to test all these other hypotheses, which is this actually a useful set of metrics, or is this a useful model that can actually help with design of shared mobility services? And I think it's a great point. If we could calculate metrics based on the output of MatSim, and then we can also look at, is there some association between those metrics, good or bad, and performance of the shared ride mobility fleet in MatSim? I think there's going to be, for sure. But of course, it's a hypothesis, so there could be no connection at all.
Thank you. Very, very interesting. So any other question from the audience? Oh, yeah, Mark.
Hey,
go
Michael.
ahead.
Yeah. Hey,
Hi.
Michael, can you guys hear me?
Yeah.
Yeah. All right, cool. Thank you for the interesting talk. I was wondering along similar lines than Joelle about the time dependency of the flows, and here in particular with respect to using MNFLOP to design fleet sizes and routes for buses or trains in a city. Do you think that the time dependence matters? I'm just thinking along the lines, the fleet that is, say, optimal in the morning may not be for, the afternoon off peak. And so an investment, how would you, build that up if your budget is constrained?
Yeah, fair question. So definitely demand is time dependent. So the shareability of the network is going to be time dependent, both in terms of overall demand, but I think maybe even more importantly into the spatial distribution demand, right? It's going to be much different in the morning compared to the evening, let alone the nighttime. So to make maybe call them tactical planning decisions, we would definitely need to incorporate time dependence. So I think the other part of your question was about, if you're budget constrained, how do you take into incorporate the time dependence? Yeah, okay, that's a really good question. So if we are using it to make connections between fleet size or the structure of routes under a budget constraint, I want to say you'd want to use some type of multi-stage stochastic program, but maybe that's the wrong way of thinking about it. Yeah, it's a real good question.
Yeah, I mean, I think it's a very hard problem, and yeah, multi-stage optimization could be used. I was just curious to hear, your thoughts about how you would use the MNFLOP results to make some actionable or give some insights or directions to a transport agency that would need to operate in the real world, and what would be possible shortcomings that you could see in the current MNFLOP formulation that you would need to overcome first.
Yeah, okay, great question. Well, I think one of the main immediate insights is that we have those link flows from the output of MNFLOP, which to me says, here's where you want to put your high capacity fixed route transit services. And of course, that could change as a function of the time of day, and a transit agency can easily flex to different routes at different times of day. Shortcomings, there are a number. I pitch it as a positive because I believe it is a positive, that this is mode agnostic or mode independent. Just simply, of course, you could get demand from a transit agency or get demand from somewhere else and just work with that demand as opposed to mode independent. But as you actually, of course, start designing these systems, that is going to change the structure of the demand by nature. So demand is actually not endogenous in any design decision that might be made, whereas you probably would want it to be. Mm-hmm. Other shortcomings, one thing we want to incorporate is, so we intentionally did not have link capacity constraints because we wanted to see how much could you force these flows onto fewer and fewer links. But if you're designing physical infrastructure on a constrained amount of space, there's an upper limit. There's no way around that, right? If you're in Manhattan, the subway going north to south can only handle so many people. So we probably should incorporate some upper end on our link capacity constraints. I think that should be relatively easy to do. It might make the problem more challenging to solve.
Yeah, waiting for a helicopter to pass at the church disappeared. Yeah, thanks for the answer. I had just the last comment that I just wanted to ask on the MNFLOP formulation. You were looking as into, say, the detour lengths as a soft constraint to the problem. You were penalizing big ones. Have you looked into making them a hard constraint and sort of say, we would not accept anything that is more than a certain percentage with respect to the shortest path or alternative formulations?
So great question. So within the formulation, it is a soft constraint, but the way we construct the K paths, it's a hard constraint. So we only allow for K shortest paths. So we set it to the 5, but actually the way we constructed it, there's actually a limit on the maximum detour, absolute maximum detour and relative maximum detour. So we could actually do paths.
So it's by the choice of K, just that okay, cool.
The construction of the K paths. Exactly.
Yeah. Okay. Thank you so much.
Thank you. Kenan?
Great discussion. Kenan, you're up next.
Yes, so my question is also regarding the first project. Oh, by the way, great presentation. Yeah, so have you tried this one on different kind of networks and see how the shareability change over the against the network structure? Because I used to read some paper looking into the shareability, but defined in a different way against the network structure and see some power law rule.
Yes, first let me, I guess, apologize for not including the lit review in the presentation, but there are, of course, as you're pointing out, other researchers that have looked at shareability from different perspectives. I guess the case we're making for ours is that they're looking at specific modes. They have capacity constraints, not even on the links, but on the vehicles themselves and things like that. So again, ours is more. So your second question, how have we looked at different networks? So yes, we tried to do Chicago after Sioux Falls, and what we found is, well, Gurobi can't handle it. We had optimality gaps of over 100%. So we're probably going to work at a medium-sized network like Anaheim or something like that. But even with Chicago, with the huge optimality gap, we are seeing significant differences in shareability potential from the northern part of Chicago into the CBD compared to the southern part of Chicago into the CBD. So structure absolutely matters. And it not only matters from an output perspective, it matters from a computational complexity perspective. So the more OD pairs with close paths, close spatial paths to each other, the harder the problem is to solve because you have more quadratic terms that come into play.
Thanks.
Excellent question.
Thank you, Kenan, for the question. Actually, I have another question related to what Mark asked for the detours, because so from the point of view of a company trying to optimize the shared routes, I understand that you want to put this as a constraint. You don't want more than a certain number of miles of detour. But on the other hand, I guess also this could be there could be a feedback loop in there, in the sense that the detour could be, if you substitute in your algorithm the assignment to this kind of reaction curves from populations that want to accept a certain price for a trip, then the detour could influence that. Like if you have to do a long detour, you will pay less. So there could be a way to hide this constraint inside of an embedded decision problem somehow.
I think you're right. Yeah, I think you could have, well, of course you can choose the complexity of your function, but you could just make the demand from an OD pair a function of the detour the traveler from that OD pair would have to traverse given the decisions you make for which path they choose. That's a really good idea. I'm afraid to even try to add complexity to the problem, but that would be a really interesting one. And I think that would allow us to move actually more towards making design decisions as opposed to kind of just being a high-level metric going on.
Absolutely, yeah. Interesting. And maybe the last question I had was, I was impressed by these. I understand the Sioux Falls was a kind of an experimental setup to test out the things, but I was a bit surprised by the 5% increase in detour. And so I wanted to kind of ask you, did you try some varying heterogeneity in demand, or was that result specific to the fact that demands were aligned in a certain way?
So we definitely tried all different demands between origin and destinations. Let me just check some of the other. Let me share my screen real quick here. So I showed another one where the detour was 5%. And then in the area we have some scenarios we have 5% again, 5% again, but then we have 14% for
Okay, I see.
scatter case. So it definitely depends on the spatial distribution of demand. One thing to note though, okay, is that if you have an origin destination pair with a lot of flow between it, you don't want to have that OD detour, right? You want to have the smaller demand OD detours detouring into the high demand. So that's why, like, even though there might be a lot of OD pairs that have detours, from a demand weighted perspective, you can get it to be a pretty small value, even at least in the Sioux network.
Yeah, it's like a conformation of demands. Like you want the less represented demand to do the detour towards the mainstream ones.
It's I guess the opposite of equitable, right? It's
yes, very interesting. Thank you. Maybe I'll allow the questions from the audience again. Is there any other question? I guess we asked a lot of questions to Michael.
That was great. Appreciate it.
Doesn't seem so. In case you have, like, I guess you gave your email address. You can reach out to him for deeper discussions. Thank you very much again, Mike. It was great having you finally here. And I wish you good luck for all the next steps in the projects you're doing, which are very exciting.
I appreciate it. And thanks again for the invitation and for having me here.
Thank you. Bye-bye. See you all next week for the next talk.
Bye, everyone.